Everyone, this video is going to go over the activity titled, "Is there a name for that?" Now before we start the activity, let's take a quick look at the learning target and the success criteria. So the goal today is to use some things we've already learned, like triangle similarity and ratios, in order to define a couple new terms, so sine, cosine, and tangent. Our success criteria, number one, I can use the side lengths of a right triangle to calculate tangent ratios to 4 decimal places. And number two, I can use the side lengths of a right triangle to calculate sine and cosine ratios to 4 decimal places. So the success criteria already kind of give a hint as to what's to come. So these things, sine, cosine, and tangent, which are new terms, are really just ratios, right? We should really call it the sine ratio, the cosine ratio, the tangent ratio. All right, so here's the activity. You've got several questions on the first page, 12 questions to get through. Your reader today is going to be number 4. Here's what you need to have for this activity. So everybody needs a copy of the activity, a ruler, a protractor. Now each table is going to get a bag of pipe cleaners. You're also going to get a sheet of paper that you're going to use when you get to question number 3. And pretty much I think that's all. Okay. So if somebody could go to the sideboard and set the timer to 25 minutes, that's how much time I want you to budget on the first page before you do the debrief. Okay. So pause the video here, work for about 25 minutes, and then when everyone's done, unpause it to watch the debrief. All right, so you've done the activity, everyone's gone over to the sideboard and you've recorded your measurements, your side lengths, your angles, and all your ratios, right? And hopefully you notice some patterns. Okay. All right, I'm going to switch over here to my quote-unquote student responses, and we're going to do a quick debrief. This debrief is going to be a little different in that we're going to work backwards. We're going to start at the bottom of the activity and work our way back up. Okay. All right, so first let's look at the values there. Okay, so hopefully you got something that looks kind of like this. Okay, so each group had a different set of pipe cleaners. We had, 3, 4, 5 inches, all the way to the last bag had 2.5, 6, and 6.5 inches. Right, so every set of pipe cleaners was unique, had a different set of measurements. Okay, but hopefully you noticed, after you got all the values on the board, that the first 4 groups had roughly the same angle measure. Okay. Now maybe you didn't get exactly 53, maybe you got 50 degrees or 55 degrees, but that's just measuring error. Okay. So for the most part, the first 4 groups had the same angle measure. The last 4 groups had the same angle measure. All right, so that's one observation. Okay, and then a second one, all right, is if you look at the ratios for the first 4 groups, they all have the same value for their ratios. And the last 4 groups have the same values for the ratios. Okay. All right. So that idea, I hope you captured, which is groups 1 through 4 had similar triangles since their ratios were the same. And then also groups that had similar triangles had the same angle measures. Okay. Now this is the idea that I want you to capture. Okay. It's that the angle measure determines what those ratios are going to be. So as long as the triangles have the same angles, they're going to end up having the same ratios. Okay. All right, so ratio is determined by the angle measure. All right, now working our way back towards the top, you had 3 different colored pipe cleaners. Okay, and so the yellow pipe cleaner was the hypotenuse of your triangle. The purple pipe cleaner was the leg that was not connected to your angle, and the red pipe cleaner was the leg that was attached to your angle. Okay. Let's draw a picture so that we can visualize what we're talking about here. So I'm using this empty space on the right side to draw my picture. Okay. Now, I want to introduce a new variable for you. So in math, we like to use x and y to represent unknown measurements. Okay? But when it comes to an angle, we like to use a special variable which isn't even one of the 26 letters in the alphabet. Okay? So this variable is a Greek letter called theta. Okay? So it looks like the number 0 with a belt. Okay. All right, so we're going to use this variable from this day forward to refer to a specific angle. All right, so we're going to put our angle in the bottom left corner of the triangle, and then now we're going to label each of the 3 sides. Okay. So first, we all know this from previous lessons, that the side that is across from the right angle is called the hypotenuse. Okay. And now I'm going to give you 2 new terms. Okay. If we look at our angle over here, and if we look at the side that is across from our angle, okay, this is called the opposite side. Okay. Now for you called that the purple side. Okay. And so just make a note here, the purple side is what we'll now refer to as the opposite side of the triangle. Okay. And then the leg that was attached or connected to the angle, that's going to be called the adjacent side. Okay. Now we were referring to it as the red side, but from now on we'll call it the adjacent side. Okay. All right. So the adjacent side is attached to the angle, the opposite side is across from the angle. Okay. All right. So we know that each side of the triangle has a special name, okay? And we can see up here that we were creating ratios using those sides. Okay? Now these ratios actually have names as well. Okay? So let's make a note here. These ratios have names. Okay. All right, before I reveal what the names are, let's convert the colors to the names of the side, right? So instead of purple, yellow, red, we'll write hypotenuse, adjacent, opposite. All right, so the purple-yellow ratio, that's going to be purple, opposite side, yellow, hypotenuse. Okay, so let's write opposite to hypotenuse, and we can abbreviate, just use the first 3 letters. All right, the red to yellow ratio, that would be now known as the adjacent to hypotenuse ratio. Okay. And then finally, the purple to red ratio, that's going to be the opposite to adjacent ratio. All right. So we're just redefining the ratios now using our new labels instead of the colors. Okay. But now let's talk about the names of these ratios. Okay. So the first ratio, right, purple to yellow or opposite to hypotenuse, this is called the sine ratio, S-I-N-E. Okay. Right, the next ratio, the red to yellow, or we'll now call it the adjacent to hypotenuse, this is called the cosine ratio. And then our third ratio, purple to red or opposite to adjacent, this is called the tangent ratio. Okay. All right, so 3 different ratios using the different sides of our right triangle. Okay. All right, before we flip over, remember that these ratios are determined by the angle. So if the triangles have the same angle measure, they're going to have the same value for their ratios. All right, so let's flip over to the back side, and we'll write a quick summary of the important ideas from this lesson. Okay. All right, so one big takeaway from today is that these ratios have names. All right, so each ratio of sides in a right triangle has a specific name. Okay. And the value of the ratio is determined by the angle measure. Oops. It's determined by the angle measure. All right. So let's go ahead and sketch a right triangle. And I'll do something a little different here. So on the front side, I place the angle here in the bottom left, but there's no rule that says it has to go there. All right. So this time I'll place the angle symbol in the top right. Okay. All right, now remember, the side across from our angle is the opposite side. Okay, should probably mark the right angle. Okay, the leg that is attached to our angle is the adjacent side. Okay. And then the longest side, which is always going to be across from the 90-degree angle, that's our hypotenuse. All right, so the three ratios, okay, their names are sine, cosine, and tangent. Okay. And remember, it's the angle that determines the ratio. Okay. So if I know the angle measure, right, then I can figure out the sine ratio. And I'm just going to look at the ratio of the opposite side to the hypotenuse. Okay. If I know the angle measure, then I can find the cosine ratio, okay, which again, that's going to be the adjacent side to the hypotenuse. Okay. And then the tangent ratio can be found if we know the angle, then the ratio will be opposite to adjacent. Now, if this is your first time hearing of these ratios, sine, cosine, and tangent, you might be wondering, well, gosh, how am I going to remember what is what? Or how am I going to remember what sides are used for which ratio? Okay. And to help you remember, somebody came up with a silly phrase, and that phrase is so katoa. Right. Just like you probably have heard the silly phrase PEMDAS, right? Or please excuse my dear Aunt Sally, whatever it is, right? That's to help you remember order of operations. Okay. So this is just a silly phrase that somebody came up with to help you remember the ratios. Okay. So in SOHCAHTOA, the S stands for sine, the C stands for cosine, the T stands for tangent. Okay. And then the other letters are for, opposite, adjacent, or hypotenuse. Okay. So for sine, we are going to do the opposite to hypotenuse ratio. For cosine, that's adjacent to hypotenuse, and for tangent, it's opposite to adjacent. Okay. All right. So let's pause the video here, keep the quick notes up for anybody who's still copying, and then I'd like you to spend the next 10 minutes completing the 4 questions in the Check Your Understanding section. Okay. So somebody can get up and put 10 minutes on our timer, and then pause the video, and then when the 10 minutes are up, go ahead and unpause so that you can check your answers. All right, so it's been 10 minutes. You've worked on the problems on the backside. Let's check answers with one another. Okay. All right, so question number 1. Okay. Notice that all of these ratios are looking at angle H. So you want to start by putting the angle symbol over here by point H. Okay. And then once you do, then you can label the opposite side, the adjacent side, and the hypotenuse. All right, so here are the ratios in numeric form: 5 to 13, 12 to 13, and 5 to 12. All right, part B is a little tricky because some of the questions want you to use F as the angle, and the other half of the questions want you to use D as the angle. So I did a little color coding here. So for the F problems, right, I put I used blue. So I have a blue angle here at F, and then I've got opposite, adjacent, hypotenuse. Okay. For the problems about D, okay, I did that in green. So now I have a green angle symbol there, and in green I've got the words opposite, adjacent, hypotenuse. All right. Question 2. So we have 4 triangles. Each triangle has an angle that's labeled with our new variable, theta. And we have some side lengths. But we're only looking for triangles whose tangent ratio is 2 to 3. Okay. And so the tangent ratio is opposite to adjacent. And so I wrote the ratio for each triangle. Okay, opposite to adjacent, opposite to adjacent, opposite to adjacent, and then opposite to adjacent. Okay. And then when I could, I tried to simplify those ratios. So 2/3 is already in simplest form. 15 to 10, right, divide by 5. 12 to 18, divide by 6. 7 to 21, divide by 7. Okay. And after simplifying, you'll see that this ratio is already 2/3. This ratio is not 2/3. It's actually the reciprocal of 2/3, so that doesn't count. Okay. The third triangle has a ratio of 2/3. The last one has a ratio of 1/3. Okay. So only 2 triangles have a tangent ratio that's opposite to adjacent of 2/3, and that's the first and the third triangle. All right, question number 3. So this question requires a little bit of prior knowledge from our last activity when we were studying the 30, 60, 90 triangles. Okay. So remember that the scale factor between the short leg and the hypotenuse is a factor of 2, and the scale factor between the short leg and the long leg is a scale factor of √3. Okay. So we can use those scale factors to find the 2 missing side lengths. So hypotenuse is 8, and the long leg is 4 times √3. Okay. Now, because it's mentioning the 30-degree angle, I went ahead and placed the angle symbol at that vertex and then labeled the sides. Okay. Opposite is across, adjacent is next to, and then the hypotenuse is the longest side. All right, now our sine ratio, that's opposite to hypotenuse, so 4 to 8, and then we can simplify that to 1/2. And it's not an accident that it's 1/2 because look, 2 is part of that scale factor, right? 2 is the reciprocal of 1/2. And we already knew that there was a scale factor of 2 to go between the short leg and the hypotenuse. So to go in the other direction, we divide by 2, which is the same as 1/2. All right. The last question, I think all we need to do here is take the information and create a picture out of it. Okay. So you can start by making a right triangle. Okay. We know the angle measure, so I just went ahead and placed that in one of the vertices. Okay. And because this says cosine, then I know that the numbers in this ratio are the adjacent and the hypotenuse. Okay. So here's the adjacent side, labeled that with the measurement 2. Here's the hypotenuse, labeled that with the measurement 7. Okay. All right. So if you have time, if there's still time in class, I'm going to ask the guest teacher to pass out your exit ticket, and then you can complete it and turn it into the basket before you leave. All right, have a great rest of your day. I'll see everybody on Friday.